It started.
All right, hello. Welcome back to another Mathcounts meeting. So we're doing 1990 state sprint problems. We're on number 15. If y equals 3z minus z cubed over 2 and z equals x squared plus 2, what is y to the nearest integer when x is 0.5? All right, so a bunch of plugging in stuff. What I would do is I would first calculate the value of z without rounding at all. So if x is 0.5, that's just 1/2, right? So if z equals x squared plus 2 and x equals 1/2, then z is going to equal 1/2 squared plus 2, or 1/4 plus 2, or 9/4. Now we can plug in 9/4 into our y equation. So y is going to equal 3 times 9/4, so 27/4, and then minus 9/4 cubed over 2. And we have to find y to the nearest integer. So perhaps I would estimate this as a decimal. Um, or maybe we can do it with fractions as well. I don't know. What do you think, Bill?
So, in this case, it's asking for y to the nearest integer. Mm, Well, is 4 cubed really like is 4 cubed is 160 is 64? Is 164 small enough that if we round it, it's gonna be insignificant? It's insignificant enough that we can round it.
Oh, what are you saying?
I'm saying that is the 9/4 cube, is that a small enough number that we can round it?
Oh, what do you mean? Ran into what?
Well, you were suggesting that we round the 9/4 cube to
No, okay, how about let's just expand the fraction, all right? Um yeah, let's just try that. Okay. So if we do 9/4 cubed, well 9 squared is going to equal 81. So 9 cubed is just 81 times 9. That's going to be it's going to be 729. And then 4 cubed is just 16 times 4, so 64. So we have 27/4 minus 729 60/4 over 2. So what do we do here? Maybe we should estimate this now. So just let's see what approximately let's put the 2 into there first. So we're gonna have 27/8 minus 729 1/28. Then maybe we should see if 729 is goes into 128 pretty closely, so we can test like 5 or something. So that's going to be 640. Um, and if we add another 128, that's going to be 768. So it looks like it's like maybe like I would say like 5.6 or 7-ish. Like judging on how close 729 is to 768 and 640. Maybe 5.7. And then 27 over 8. That's just gonna be, so 24 over 8 is 3. So that's just gonna be 3 plus 3/8. So like uh 3.375 minus 5.7. Did I do that right?
Mm, yeah, looks like it. Yeah.
Okay. I'm gonna see on my calculator if I did it pretty well. Okay. Oh wow. So yeah, 729 over 128 is very close to 5.7, and 27 over 8 is just 3.375. And then now, well, we can just subtract them. So this is gonna be 5. So there's a 10 here. So we have to put this down. That's a 6, and then we have two tens. Or actually, this is gonna be a 9. And then there's a 10 here, 9, 2, 633, and then 2.325. But this is actually negative because we're doing 3.375 minus 5.7. So we get y is approximately equal to negative 2.325. So we want the nearest integer to this. So the nearest integer to this is going to be negative 2, right? Um, like, yeah, it's not negative 3 because that would be like you're going down like about 0.7. But to get to negative 2, you're only going up like point 0.3. Yeah. So your answer should be negative 2. Yeah, that's the answer. Um, Anything you want to add, Bill? Should we try approximating it as a decimal first?
Approximating as a decimal. Um, in this case, because we're cubing it this much, I feel like approximating it by a decimal might change the result far enough that it will go over and become another number. Because
Yeah,
2.3 something, that's not all that far away from 2.5. So I'm afraid that if we just approximate a decimal too early on, then we might face the chance that we'll go over 2.5.
yeah, but I don't know. Like, why was this? The solution that we did is like pretty messy. I mean, I'm just wondering if there's like a better solution.
I mean, to be honest, I think we could have just straight up done the problem without approximations and then do maybe approximations to integer as the last step. So we just changed the 27 over 8 to something over 128, and then we did the subtraction, and then from there we can estimate which multiple of 128 is the closest to.
Yeah, yeah, I know, but like that still seems like pretty messy to me. Like you're still working with like kind of big numbers, and it's just like not very elegant. I don't know. Maybe this is the best way, but I don't know. I'm not sure. But I mean, doing this is fine. It doesn't take that long. All right, let's just move on then. Um, Kathy earns $3.55 per hour and receives a 15-cent per hour pay raise every 6 months. Jack earns $6.05 per hour and has a pay decrease of 10 cents per hour every 6 months. How many years will it be until they earn the same hourly rate wage? All right, so we have some linear equation problems. So let's just say every 6 months we denote it as a one increase in x. So if a year has gone by, x will equal 2. So with that, we can model Kathy's earnings per hour as her initial $3.55 per hour, and then an increase of 15 cents per 6 months. And we define x to be like that, so you can just put x. And then Jack is going to be his initial $6.05, and then he gets paid decrease of 10 cents every 6 months. And we want to know when they will earn the same hourly wage. So we just equate these expressions. Actually, I'm going to drop these dollar signs, just assume everything is in dollars. Um, okay, my handwriting is a little bit bad, but yeah, move x to one side, move constants to the other side. So we have minus 0.1x, we add 0.1x to both sides. We're going to get 0.25x on this side. And then we subtract 3.55 from 6.05. So that will give us 2.50. Yeah. And then now we just divide both sides by 0.25. So x is going to equal 2.50 over 0.25. So you can multiply top and bottom by 100, moving the decimal place 2 places to the right. So that will give us 250 over 25. So that is just 10. And we define x as every 6 months, right? So there are 2 6 months in a year. So if we have 10 6 months, it will take 5 years for them to have the same hourly rates. And that's the answer.
Okay, so
Oh yeah.
another way you can do this, if you want to like a better way to, I feel like this will be a quicker way if you're able to visualize it. So if you were if you were to think of it as, so the one person is earning 2.5 dollars more per hour than the other person, and then each six months, one person is moving up 0.15, the other person is moving down 0.1. So they're coming closer together, $0.25 each every 6 months, and they need to come together $2.5. So that'll take 10 6 months, and so that's five years.
Yeah. Yeah, so basically like the same thing we did here, but like uh I don't even know. Like yeah, it's basically the same thing we
Yeah,
did
but
here.
if you can just like visualize it this way, you
But
don't
like yeah,
you don't really
if you
have
think of
to
it that way,
if you don't have to
uh
really deal with like equations and stuff.
yeah, like if you think of it that way, you might be able to do it a bit faster. Yeah. All right, number 17, find all integer values of x for which the equation x plus 3 times x minus 2 is less than 0 is true. All right. So x is going to be an integer. We have to find all value of the x that satisfies this expression right here. So, all right. So whenever you have like uh expressions like multiplying by each other, like like I don't know, like when you have stuff multiplying by each other and you have an inequality with a 0 on the other side, like all you're looking at here are like the signs of these multiplying expressions, right? Like if these were both positive, that would not satisfy the expression because this is positive, and a positive number cannot be less than 0. And same thing if they're both negative, because then they multiply to a positive number. So what we're looking for here is just so that one of these expressions is positive and the other one is negative. And then, so with that in mind, you should look at your I don't know how to describe it. Like, you should look at when these equal to zero, because that will be like your limiting cases, kind of like once you pass those thresholds, something is going to change about them. Like, basically, we can visualize it on a number line, okay? And then we have x equals -3 here and x equals 2 here, right? So whenever we are at x equals -3, this is going to be 0, and this is going to be a negative number. So we'll denote this as 0. And then once we go lower than -3, this will turn negative, and this will stay negative, right? Because we have both positive x's here. So on this side, it will stay double negative forever. And then let's look at 2. So 2 is going to be, it's going to be 0 for this here, and it's going to be positive for this here, right? So there's going to be 0 here. And then beyond 2, this will get positive, and this will stay positive, right? So beyond 2, we're going to have positive, positive. And then in the middle here, what's going to happen? Well, x is going to be less than 2, so this expression has to be negative, and x is going to be greater than -3, so this expression has to be positive. So we're going to have positive, negative. Now, what did we say before? We were looking at the signs of the expressions. We want it where they're alternating signs so that it equals a negative number, so that it's less than 0. So now we find out that we're just looking at this region, right? And we just need to find all integers in this region, and that's going to be our solution. Now, it can't be -3 and 2 because they equal 0, and we need it to be strictly less than 0. And then so we're just looking for the integers between -3 and 2, non-inclusive. So that's going to be -2, -1, 0, 1. That's your answer. Yeah, anything you want to say, Bill?
Yeah, not really.
So I'm gonna add on something to here. So this is a
Quadratic.
yeah, it's a quadratic, and it's a very useful thing for like when you're solving quadratic inequalities. So like I don't know, can I make an example here?
Sure.
So let's just say you had x squared plus no. Okay, let's say you had uh let's say you had x squared minus 2x minus 4 is less than um negative 6x minus 8. All right. Okay, so whenever you have quadratic inequalities and you're like solving them or whatever, putting it into this form where you have the factors multiplying and it's like less than or greater than or whatever to 0, like that's a very good form to put it in. It's way easier to solve it this way than like looking at it like this, right? So yeah, we should do that. And how we should do that is first get the 0 um on one side. So we're going to move everything to this side. So once we do that, that will give us x squared plus 4x plus 4 is less than 0. And then we want to factor it because that's going to make it easier to work with, because then we're just looking at the signs of the factors, right? And not like that would be harder. Or I mean, you could use like the quadratic formula, but like whatever. So factor this, right? It's going to be x plus 2 times x plus 2. Oh, this is actually a perfect square. So there are no solutions. Okay, but whatever. So like yeah, you want to put it into this form and it'll be easier to solve. But like, if we had I don't know, uh uh x squared plus 3x plus 2 is less than 0, then that would factor to x plus 2 times x plus 1 is less than 0. And then this would be easier to solve, right? Then we're just doing the same thing that we did before.
Okay. So for this problem, if you look at the equation given to you, x plus 3 times x minus 2, if you can think of it like the quadratic graph, it opens upwards and it has zeros at -3 and 2. So if it opens upwards and has zeros at -3 and 2, you know that the negative part is going to be between -3 and 2, and you can use that to find your
Yeah,
answer.
yeah. All right. Let's just move on then. Okay. Okay, so a formula is programmed into a computer. It reads in the following input stuff and output stuff. If the same formula is used, what would be the output value of 14 is entered? All right, so we don't know what the formula is, and we're given a sequence where the formula is applied. So we're basically looking for a pattern in the sequence. So there are two types of sequences that we should always check first. That's arithmetic and geometric. Arithmetic. You pronounce it arithmetic, right? Uh, okay,
I
whatever.
pronounce it both ways, actually. I've pronounced it both ways.
Arithmetic sequence, arithmetic sequence. I think it's arithmetic.
Well, in different situations, I'll say it different ways. In this case, I pronounce it arithmetic sequence.
Okay, well, whatever. Yeah. So arithmetic and geometric sequence. You always want to check these sequences because they're very common sequences. And what are these sequences? Well, arithmetic sequences are just a sequence that's being a constant is being added to every term. So an example of an arithmetic sequence could be, like 1, 2, 3, 4, and so on, because every term is being added by 1. But it doesn't have to be like addition, it can also be subtraction. So it could be like 2, 0, -2, -4, right? So that's I don't know, that should be pretty simple. And geometric sequence is a sequence where you are multiplying by something every term. So that could be something like 1, 2, 4, 8, and so on. You're multiplying by 2, but it doesn't have to be multiplying by a positive number. It can also be multiplying by a negative number to where you have, 1, -2, 4, and then -8. So that would be multiplying by -2 um, every term, but it also doesn't have to be um, increasing. You can also multiply by a fraction every term. So you could have 1, 1/3, 1/9, and so on. So you're multiplying by 1/3 every term, and it's decreasing. So yeah, you want to check for these type of sequences because they are common. All right, so we should look at the 4, 5, 6 first because they are one apart, right? So if they are one apart, we can check for stuff easier than checking a term that is farther, because then you have to like you have to take that into account and it'll be like harder, right? So let's just look at this. Let's check if it has an arithmetic progression. So from 23 to 34, I mean not what 23 to 32, you're adding 9, and 32 to 43, but you're adding 11 now, right? So it's not an arithmetic sequence, and it's also not a geometric sequence, because to get to 23 to 32, you'd have to multiply 23 by 32 over 23, right? So that the 23's cancel and you have 32. Now, if you multiply 32 by 32 over 23, you're obviously not going to get 43, because you can't cancel out with 23, because 32 is a factor of or it's a power of 2, and 23 is a prime. So it's not geometric. So so now I guess we should explain more types of sequences. So there are quadratic sequences, and quadratic sequences is where it's like an arithmetic sequence, but the constant that you're adding changes also by a constant every term. So a quadratic sequence could be like 1, 2, 4, 8, and so on. No, not 8. 1, 2, 7. My bad. So you're adding 1, and then you're adding 2, and then you're adding 3. And then so your terms, uh, Bill,
Yes.
I'm doing this right, am I?
Uh, uh, y- uh, yes. Yes, you are. Yeah, you are.
Okay. But like, shouldn't this be 8 because
What?
this would model like x squared because it's
No, if it's
quadratic.
x squared, the first one will be plus 3. If it's x squared, it will be
Oh, okay, yeah, yeah, I'm done.
plus 3 plus 5
Oh,
plus
okay, okay,
7
okay,
plus
yeah,
8.
okay. Okay, yeah. So this would be a quadratic sequence because so from 1 to 2 you're adding 1, from 2 to 4 you're adding 2, and from 4 to 7 you're adding 3. And in each of these addings you're adding 1. And then these have to be constant for it to be quadratic. Okay? Um so it looks plausible that we have a quadratic sequence, but like we can't know for sure, and we have to use the 10th number, which is 107. So, all right. So can I erase this? Oh, no. All right. Okay. Um let's just write it out instead of doing stuff. So on our 7th number, we if this were quadratic, then our increasing stuff would have to increase by 2 every time, right? So our 7th number here, let me just, can I move this? Uh, let's just delete it. All right. Okay, so if it's quadratic, we're checking, its terms has to increase by 2 every time. The increasing constant has to increase by 2 every time. So from 6 to 7, it has to be plus 13. And from 7 to 8, it has to be plus 15. And from 8 to 9, it has to be plus 17. And from 9 to 10, it has to be plus 19. Um, and then, so how we're going to check this is we're going to add up all of these plus 43. And if it equals 107, then this is the sequence that we have. So let's just do that. We have 43, 13, 15, oh man. Okay, 13, 15, 17, 19. So 17 and 13 give 30, right? And then 43 and 15 is going to be 58. So that's going to be 88 plus 19 is going to be 107. Oh, and it equals 107. So this is our sequence. Um, okay, so and it's saying if the so yeah, it's saying if the same formula is used, what would be the output value if 14 is entered? Um, I guess I would just I feel like writing the equation for this would take more time than just listing it out. What do you think, Bill?
If you can, If you're trying to brute force the equation, yes, but there is something you can notice. I don't know if you guys can notice this or will be able to notice this or not, but if you can notice it, then you would probably be able to get the equation faster.
Wait,
So,
notice what?
so a normal x squared is, I the amount is in a normal y equals x squared. The amount is increasing by 2 each time. And here it's doing the same thing, it's increasing by 2 each time. So we know that this is a quadratic with a coefficient of x squared is 1. So also if we look here, in a normal x squared, 4 squared is 16 and 5 squared is 25. So the difference is 9. So the difference between the fourth number and the fifth number is 9. And here it's also 9. So we know that it's just x squared and then shifted up 7 places. The equation for this is x squared plus 7. But that's pretty hard to notice unless you know what to look for.
Um, yeah, yeah. Yeah, you can also figure it out like that. I don't know. If you're good at like doing that,
If
maybe you should do it.
y-
But
if you can like
it,
if you can see it right away, then you should do it. But if you can't like if you don't notice it right away, you then what 14 is not that far away.
yeah,
You should just do it up to
br- br-
14.
yeah, brute forcing is not that bad. Yeah, but if you can find the equation, it might be a bit faster. Or maybe you can even notice it from like not doing this at all, just like looking at that, but whatever. Okay, so yeah, if you do it Bill's way, it's going to be pretty obvious, right? So um you figure out the equation to be x squared plus 7, and then you plug in 14. 14 squared is going to be 196 plus 7, that's going to be 203. And then let's try brute forcing it. So we're going to add 21 to 11, and then we're going to add 23 to 12, and then to 13 we're going to add 25, and then to 14 we're going to add 27. And then we need to add all of these terms together. Let's just take out 20s from all of them, right? So that's going to be 80. So we're going to have 187. And then plus 1, plus 3, plus 5, plus 7. Well, this is, if you have addition of odd numbers, it's actually going to be a perfect square if you start from 1. And so, it, if you have one term, it's going to be 1 squared. If you have two terms, it's going to be 2 squared. So this 1 plus 3 plus 5 plus 7 is going to equal 4 squared or 16. But obviously, if you don't know that, you could just, add the numbers. Okay, so 187 plus 16, that's going to be 203. And the same thing that we got before, the answer is 203. All right. This is a bit of a tall problem. I'll just expand this a bit. Okay. It's pretty good.
Amazing.
So the rectangular region shown on the left is cut on the dotted line and reassembled to form the figure on the right. What is the area of the figure shown on the right? What the?
This is
Uh, okay, that is actually so
I
easy.
know this is extremely easy.
Um, okay. All right.
This is
So
suspiciously easy.
Uh, well, it gives us the right answer.
Oh, that's true.
All right. So the thing to notice here is that, if you have like shapes and stuff, and you move things around, but you don't ever like take a piece away, or you add a piece in that wasn't in it before, then the area is going to stay the same, right? So, it even like gives us the thing before. Um, so the area of this is just going to be the area of this, right? This is just rectangle with side 3, side 6. So this area is going to be 18. We just move stuff around to get that. So the area of this is also going to be 18. All right, that was um, suspiciously easy.
Yes, that question, if it came up, honestly, I would be a bit suspicious because that's way too easy. So you should,
I
if
mean, I would still do it like that
yeah, you would
because
do
it's
it like that,
obviously the
but
solution.
if it's that easy, you should probably reread the question to
Oh
make
yeah,
sure you
okay, yeah.
understand.
So yeah, if you see that like I don't know something like weird or like something suspicious or whatever, then make sure like I don't know, just like read it again, make sure you understand what's happening. Um, but yeah, but I guess it can just be that easy sometimes. Okay. Express the following as a simple reduced rational number. We have this. I forgot what this was called, but I don't know. I'll call it the fraction tower. Okay, so we have a fraction tower. These aren't hard. You just go through every step. So 1 plus 1/2 is going to equal 3 halves. So in this thing right here, it's going to be 2 over 3 halves. And if you're dividing by a fraction, then you're multiplying by its reciprocal. So 2 times 2/3 is going to equal 4/3. So now we have 1 over 2 minus 1 over 1 plus 4/3. 1 plus 4/3 is just 7/3. And you have 1 over 7/3, that's going to flip it. So you're going to have 3/7. So 1 over 2 minus 3/7. Just 14/7 minus 3/7, that's going to be 11/7. 1 over a fraction is going to flip it, so we're going to have 7/11. Yep, that's the answer. All right, two typists working together can type a paper in 5 hours. The faster typist can complete the paper in 9 hours. How many hours will it take the slower typist to complete the paper alone? Express your answer as a mixed number. All right, so it's one of those questions. All right, so okay. So when they're working together, it takes 5 hours, and the faster one out of them completes the paper in 9 hours. And how many hours? Okay, and then you wanna know how many hours it will take the slower typist to complete the paper alone. All right, so like the rate of the faster typist is a paper per 9 hours. So it's like uh if you had x as the number of hours, 1/9 x would give the number of papers that the faster typist completes because it's one every 9 hours. And then the two typists working together types a paper in 5 hours. So that means like their rate is 1/5 x because every 5 hours they're going to type a paper. And then you're adding something to here, right, to get this rate. Um, so let's say k is like the rate of the slower typer. You're adding this to the faster typer's rate to get their combined rate, and then you cancel out x. You're just gonna go 1/9 plus k equals 1/5. K equals 1/5 minus 1/9. So that's just going to be 9 over 45 minus 5 over 45. That's going to equal 4 over 45. Did I even do that right? Uh,
Yes.
oh, okay, I get it. Yeah, okay. So we got 4 over 45 is the slower typist's rate, right? So, um, like basically it's saying every 45 hours the typist will type 4 papers, right? And we want to know how many hours it will take for them to complete the paper. So that's going to be the reciprocal of this fraction, right? 45/4. And it says expressed as a mixed number. You take out a 44, that's going to be 4, 1/4. So 4 and 1/4. No, oh my, I'm so bad. Uh, so you take out a 44, 44 over 4 is 11, and that will leave a 1 on top, so 11 and 1/4. Um, Anything you want to say, Bill?
Not particularly, just yeah. I mean, what Austin
Yeah,
said basically is that's probably like the only way you would do this.
yeah, sure. All right, express the sum as a base 10. Why do they have it in words? That I've never seen that in my life.
They have it in words. Who puts it in words? What?
All right. Okay. So let's explain bases if you guys don't know bases. Um, so if you have a number, let's just say 121, if you have a subscript on the number, this denotes the base of the number. Okay. Um, so like if I had 121 with a subscript of 7, this means 121 with a base of 7. Now, what do bases mean? So bases mean, okay, it's like this. Um, when we have a number in our base 10 world, let's say 121 for instance, the actual numerical value of the 121 is going to be each digit times some power of 10, and the more left it is, the higher power of 10 is going to be multiplied by. So like the 1 is going to be multiplied by 10 to the 0, and the 2 is going to be multiplied by 10 to the first, and the 1 is going to be multiplied by 10 squared, right? So like the actual like numerical value of it is 100 plus 20 plus 1, which equals 121. Well, I mean, it's the same thing because we're working at base 10, right? I don't know. It seems a little bit confusing when you're talking about it in base 10. But if you have a number in a different base, this is not its actual. Okay, so let's say we had it in base 7. This is not its actual numerical value. How you get its numerical value is like what we did here. You're going to multiply by 7 to the 0. You're going to multiply by 7 to the first. And you're going to multiply by 7 squared. So you're going to get 49, 14, and 1. And then you add these. And then this is going to be like the the actual numerical value denoted in base 10. So um so so like basically you're converting it to base 10. Um if you do this. So then this is just going to equal 64. So we just found out that 121 in base 7 is going to equal 64 in base 10. Um, there's a lot of way to explain bases. Um, I mean, if you just think of it like this, you're multiplying by powers on the place values. You should be fine with doing stuff. Anything you want to say about bases, Bill?
Mm, no. About bases,
Um,
yeah, bases are a bit confusing, but once you get used to them, they aren't that bad.
yeah, okay. And one thing to note is that on your base, if we have any number base 7, none of the digits can be 7 or greater, right? Like think of our base 10 world. Our base 10 world, we have 10 digits, right? And the highest of which is 9, which is one less than 10, right? It wouldn't make sense in our base 10 rule to have a digit of 10, right? If you have a digit of 10, then just carry over the 1 to the next place value. So in bases, you can't have that you can't have that number, you can't have that base in the digit, and you can't have any number greater than this base also in the digit. That I don't know, that might be useful sometime. And if you're so if you're converting a different base to base 10, it's pretty easy, right? You just do what I said. You multiply by the powers of the base that you have. If you're converting from base 10 to a different base, it's a little bit different. So let's say we had 64 in base 10, or it doesn't have to be 64. Let's just do I don't know. Give me a number, Bill. Not too big.
21.
That's a little bit too small. I don't know.
Okay. Um, 54.
Okay, 54. And what base do you want to convert it in?
7.
7, sure. Okay, so we have 54 in base 10, and we want to convert it into something in base 7. So to do this, we're basically dismantling this thing backwards. So we're looking at um, powers of 7 that go into this, and the number of it, that's how many we write down. So we're going to try the biggest power of 7 that goes into this. So that would be 49, right? If you did the next power of 7, that would be way too big. So 1 power of 7 squared can go into here. So that means on our 7 squared place value, we're going to have a digit of 1, because 149 goes into 54. And then once 149 goes into 54, we subtract it, and we'll get a remainder of 5, okay? And then we check the next power of 7, which is 7 to the first, which is 7. We see if any of these can go into here, which none of it can, right? So we're gonna have a 0 here. And then we look at the final power of 7 to the 0, which is just 1. You look at how many 1s can go into 5. Well, 5, right? So this digit is going to be 5. And then so we're going to have none left. So that's how you convert it from base 10 to a different base. And if we're converting between two different bases that are not base 10, then you would probably do it in 2 steps, which would be to convert the number into base 10, and then to convert that base 10 number into the other base. There's a little trick if you have conversion of bases to bases that are a power of that base. But I don't know. You probably won't. It's not that useful. I'm not going to talk about it. But yeah, whatever. Just never mind. Okay, back to our actual problem. Where is it? Oh, it's right here. Express the sum as a base 10 numeral. So we have 11 base 2 plus 11 base 3 plus 11 base 4 plus ... to plus 11 base 12. Now, okay, we see that 11 just has digits of 1, right? So it's not going to break any of these bases, right? Like, in base 2 you can only have digits of 1 and 0, but that's satisfied here. So we're good with that. But okay, so we want to convert it into a base 10 numeral. Now remember how we converted a different base into a base 10 numeral earlier? Well, we're going to apply the same thing here, right? So let's look at 11 base 2 first, right? To convert this into base 10, we will multiply this 1 by 2 to the 0. We will multiply this 1 by 2, right? So then we would get 2 plus 1, which equals 3. So 11 in base 2 will equal 3. Well, I shouldn't say 11, but 1 in base 2 equals 3 in base 10. Now, so we can do this in a lot of ways. Something that we can see here is that this, for the 1 in this place value, for all of these numbers, it's going to equal 1, right? Because you're multiplying by that base to the 0th power, which is always going to equal 1, right? So we can go ahead and take that out. And, if we have 1 from every one of these, then we're going to have a plus 11 from all of that, right? Because we have 11 different numbers in here. So after we take that 1 out, then we just have 10 base 2, or not 10, 1 0 base 2, 1 0 base 2, plus 1 0 base 3, plus 1 0 base 4, plus dot dot dot, plus 1 0 base 12. Okay, and remember we took out all the ones, and that was equal to 11, right? So we had to remember to add the 11 at the end. Now, doing these, we can see another pattern, right? So, I mean, they all have the same thing. And what you're doing with this is you're just multiplying by the base, right? So the value of each of these is going to be 1 times the base, which is just going to be the base, right? So each of these is just going to be the base. This is going to equal 2, this is going to equal 3, this is going to equal 4, and so on, plus all the way to 12, right? And then we have the 11 at the end. So now this is just an arithmetic sequence. We can just use our arithmetic sequence formulas and stuff. So our arithmetic sequence formula is you multiply the median or the mean, because the median and the mean of the arithmetic sequence are the same, and then you multiply it by the number of terms, and then you divide it by 2. So that is the formula for a sum of the arithmetic sequence. All right, so our number of terms is going to be 11. Our median or mean is just going to be the average of the first and last two numbers. So that's going to be 14 over 2, or 7. And then we're dividing it by 2. Oh, did I miss out? I think I messed up somewhere. Like if
What did you do?
cause like this is an integer, right? But this is not going to be an integer.
11 times 7. Why are you dividing it by 2 again? You've already divided by 2 when you did the 2 plus 12, and then you turned it into 7. You already divided by 2 there.
Oh,
You don't have
okay.
to divide by 2
Yeah,
again.
I'm bad. You're okay. You're not supposed to divide by 2. I just got that confused because you're dividing it by 2 on the making the mean thingy. Okay, so this is the actual formula for the sum of the arithmetic sequence. Ignore the dividing by 2 that I was saying earlier. So the number of terms we have is 11, okay? And then to figure out the median or mean, you can do that by taking the average of the first and last number. So that's going to be 14 over 2, or times 7. And then you're going to add 11. So this is just going to be 77 plus 11. It's going to equal 88. Yeah. Yeah, I mean, there are probably more ways to do this, but this is pretty easy. Okay, anything you want to say, Bill?
Yeah, not really.
Okay, do you want to do one more problem or end it here? Oh, Bill?
Yeah, let's end it here.
Okay, yeah, sure. All right, yeah, so that's gonna be it for today. Let us know if you have any questions, or we'd also appreciate feedback if you guys think we're going like too slow or too fast or whatever. And then we'll change our how fast we go and stuff. But yeah, thanks for watching and goodbye.